Assalamualaikum. Today is on lecture 17 and this is an application of the previous lecture. So this lecture is all about the diagonalization of a matrix. So you saw in the previous lecture that ax equals to lambda x whenever x is an eigenvector. So that eigenvector is multiplied by a scalar number that is called the eigenvalue. So it is only multiplied by a scalar. So all the difficulties of matrices are swept away, right? So if you want to multiply this vector x by, let's say, 100 times, you can actually follow the eigenvector separately, and it is like having a diagonal matrix with no off-diagonal interconnection. So what does this mean? We will see in this lecture. So this is where the concept of diagonalization comes. So suppose you have n by n matrix. So in that n by n matrix you have n separate eigenvalues. So for n separate eigenvalues you have n eigenvectors. Okay. So n eigenvectors, let's say those eigenvectors are x1, x2 up to xn. So if you stack these eigenvectors into one single matrix, then you have a matrix like this to xn. So all the eigenvectors are like the columns of this matrix, and these n eigenvectors form a basis for n-dimensional space, right? Now what happens if you multiply this S matrix with A? So you have AS equals to A into x1, x2 up to xn. But we already know that Ax equals to lambda x, right? So for this, if we use this, so A is multiplied by all the columns. So if we use this formula, we have lambda 1 x1, then lambda 2 x2 to lambda n xn, all the columns. Right. So if you again divide this matrix into two parts, you have you have S at the left and this x1 is multiplied by lambda 1. So the first element of the diagonal is lambda 1 and all the other elements are 0, and all the element below this lambda 1 is 0 as well. So for multiplying x2 with lambda 2, you have to have lambda 2 at the diagonal and all the other elements are 0. So like this would be a full diagonal matrix, and all the other elements of this matrix other than the diagonal would be 0. So as this is S and this is basically a matrix of lambda, so let's say this is a capital lambda, so this is S lambda. So we have AS equals to S lambda. So if we multiply if we multiply s lambda equals to s lambda s inverse, then we have a equals to s lambda s inverse. Of course s has to be invertible in this case. So in this case S is an eigenvector matrix, S inverse is the inverse of that particular matrix, and lambda is the diagonal matrix, right? The diagonal matrix with all the eigenvalues on its diagonal. So this is why this is called the diagonalization of a matrix. But to diagonalize a matrix, you need to have the eigenvector matrix invertible, right? So how to tell that S is an invertible matrix? We saw in the previous lecture that in some cases the eigenvalues are all the same, and for those same eigenvalues you get the same eigenvectors. So if you have two eigenvectors common, then if you put those eigenvectors inside this S, then you know that if two columns of a particular matrix is same, then that you can say that not all the columns are independent. So in that case you cannot get S as an invertible matrix, right? So be careful about that all the columns of S need to be independent, and for that condition you will get S inverse, or you will get S as an invertible matrix. Now why did we convert A into this format? Because if we now multiply A square, that means A into A, so you have S lambda S inverse into S lambda S inverse. So you have S inverse and S cancelling out each other, so you'll have S lambda square S inverse. So if you have A cube, you will get S lambda cube S inverse. So if you have A to the power k, you will have S lambda to the power k S inverse. So the matrix multiplication, or the power of the matrix, has become really easy to compute, to calculate. So let's say you have a matrix A equals to 1 0 5 6. So as this is a triangular matrix, so the eigenvalues would be lambda 1 equals to 1, and then lambda 2 equals to 6. So for lambda 1 you will have the eigenvector x1 as 1 0. Okay. So for lambda 1 you need to calculate determinant of A minus lambda I. So it should be 1 minus 1 5 0 6 minus 1. So the determinant of this, so you have 0 5 0 5. So one eigenvector from this would be s1, so this is equals to 0, so this would be 0 0 as well. So for this particular matrix, one solution would be x1 equals to 1 0, and similarly for lambda 2, one particular eigenvector would be 1 1. So eigenvector matrix would be 1 0 and 1 1. So if you so the power of a, so a to the power k would be s lambda to the power k s inverse. So S inverse from this matrix would be the determinant is 1, so 1 negative 1 and 0 1, so it should be 1 0 1 1 0 1 1 and lambda to the power k. So lambda is the matrix with the eigenvalues on its diagonal. So 1 0 0 6 to the power k and 1 0 negative 1 1. So it should be 1 0 1 1. Here 1 to the power k is 1 0 0 6 to the power k and 1 0 negative 1 1. So if you want to calculate 1000 1 to the power 1000, then it has become really easy. It will need less time, it will need less computational power. Otherwise, if you try to multiply this a 1000 times manually, then you will need a lot of time, a lot more computational power. So nothing is worse than that. So after diagonalization, the computation has become really easy. And in many realistic problems, real life problems, you can apply this concept of diagonalization and can easily solve these problems. So in your future studies, you'll see a lot of use of the difference equations like u of, so in many cases you'll see a lot of sequence maintaining this equation u of k plus 1 equals to a into u of k. So that means in a sequence, if you have a vector of terms uk, then if you multiply that with a matrix, then you will get the next term, right? So in each step, it is multiplied by a, right? So u of k plus 2 would be a into u of k plus 1. It goes like this. So basically u of k is a to the power k u naught. So you'll see an example like this. So in real life problems, if you can formulate a vector like this u naught, and if you try to find a relation with this matrix with this vector, with this, so you try to find out the relation between a matrix and your formed vector, then you can calculate, or you can find out any term up to infinity. Okay. For example, if we try to work out with Fibonacci series, so we all know what is a Fibonacci sequence, right? So it goes like this: 0 1 1 2 3 5 8 8 13. It goes like this. So yeah, so the Fibonacci sequence goes like 0 1, and every other term is basically the sum of the previous two terms. So 0 and 1 sums up to 1, 1 and 1 is 2, 2 is 2 and 1 is 3, then 5, then 8, then 13. Let's say I wanted to find out the 100th term of Fibonacci sequence. So how to do that? So if you try to manually find it out, then it will be very hectic, right? So for Fibonacci, for Fibonacci, this sequence follows this equation: f of k plus 2 equals to f of k plus 1 plus f of k. So we somehow need to put this series into this formulation: u of k equals to a to the power k and u naught, right? Where u naught is a vector. And we try to find out the relationship between u naught and this matrix A. So to fit it into this relation, we need to apply a trick, right? So how to apply that trick? So we need, let's say we have f of k plus 1 equals to f of k plus 1. So this is just a dummy line to create a 2 by 1 vector. Okay, so if you consider this as the left hand side and this as the right hand side, then let's say u of k plus 1 equals to f of k plus 2 and f of k plus 1. So this is our left hand side, and our right hand side is f of, so this equals to f of k plus 1 plus f of k and f of k plus 1. So if you try to express this matrix, sorry, this is a vector, this is a 2 by 1 vector. So if you try to express this vector into matrix vector multiplication, you can write this as, so let's say the vector is f of k plus 1 and f of k. Then you can, what will be the matrix? So according to the very basic rule of matrix multiplication, it should be 1 and 1. So 1 into f of k plus 1 plus f of k is the first row, and 1 and 0. So it should be 1 into f of k plus 1 plus 0. So this one. So our u of k plus 1 is basically, so if this is u of k plus 1, then what should be u of k? So u of k is f of k plus 1, f of k plus 1 f of k plus 1 and f of k, according to this. Okay, why did you say this is f of k plus u of k plus 1? Because if you look at this, look at the first two terms, this would be said as u naught, and in u naught you will have this vector 1 and 0. So this is basically f of 0th term, and this is f of 1 term. Okay. So following that, u of k would be containing f k in the second row and f of k plus 1 in the first row. Okay. So we have this formula here: u of k plus 1 equals to A. So this is our matrix A. and we have u of k here. So we have formulated the Fibonacci sequence into our desired terms. Okay. So according to this formula, we have u naught equals to 1 0, the first and the second term. So u1 should be a into u naught. So this would be 1 1 1 0 into u naught, that means 1 0. So this would be 1 and 1. So this is the f1th term and this is the f2 term. u2 should be a into u1, that means a, so u1 was a into u naught, so a into u naught, so it should be a square u naught. So it should be 1 1 1 0 square, then 1 0. So if you do it manually, you'll have something like 1 2 1 0. I'm not sure if this is right or wrong. I hope this is right. So it should be okay. So let's do this. 1 1 1 0 and 1 1 1 0. So it should be, and so it should be 2 here, then 1 here, then 1 here, and 1 here. So I did the mistake. So it should be 2 1 1 1. So the u2 should be 2 here and 1 here. Yeah. So this is f2 and this is f3, right? So we need to find out the 100th term, right? So we have u2 as, so when we have u2, we have f2 here. So we can basically find one u100. So in u100, in u100 you have f101 and f100. But in that case, what you need to do, that you have to find out the 100th power of a multiplied with u0. Then yeah, so this is where the concept of diagonalization comes. So you need to diagonalize this matrix A, right? So we have A equals to 1 1 1 0 and the eigenvalues of this matrix are, we need to find out the eigenvalues as well, and then we need to find out the eigenvector. So to find the eigenvalues, if you could remember from the last lecture, is 1 minus lambda I equals to 1 minus lambda to 1 1 minus lambda. So the determinant of a minus lambda I equals to 0. So from this, the determinant of a minus lambda I should be lambda square minus lambda minus 1. So this is equals to 0. Lambda square minus lambda minus 1 equals to 0. So from the quadratic formula, we know that x equals to minus b plus minus root over b square minus 4ac divided by twice a. So from this, lambda 1 would be 1. Okay, so lambda would be 1 plus minus root over 5 divided by 2. So lambda 1 should be 1 plus root over 5 divided by 2, and lambda 2 should be 1 minus root over 5 divided by 2, right? So the eigen so to find the eigenvectors, we have 1 minus lambda, lambda 1 into 1 minus lambda. So we have for lambda, so this part would have the value, this lambda 1 would have the value of, okay, let's not work with the fractional values because this will have some fractional value. These two things would have fractional value, so we want to avoid the fractional value. So our eigenvalues, eigenvectors would be x1 equals to lambda 1 in the first row and 1 in the second row, and x2 would be lambda 2 in the first row and 1 in the second row. So so our eigenvector matrix would be S equals to lambda 1 1 and lambda 2 1, right? And S inverse would be 1 divided by AD minus BC, so 1 divided by lambda 1 minus lambda 2, and for inversing it would be 1 lambda 1 and negative lambda 2 and negative 1. So we had A equals to S lambda S inverse, so we need to find out the lambda here. So the lambda would be, the lambda is basically the eigenvalues on the diagonal, so it would be lambda 1 0 0 lambda 2. So we have A equals to S, which is, okay, let me clear this out. Okay, so our A would be S lambda and S inverse. So S is basically lambda 1 lambda 2 1 1 and lambda is lambda 1 0 0 lambda 2, and S inverse is basically 1 divided by lambda 1 minus lambda 2, and equals 1 minus lambda 2 and negative 1 lambda 1. I hope this is not incorrect. Okay, so this is our A matrix formulated into diagonalization. So we have 1 divided by lambda 1 minus lambda 2, then we have lambda 1, lambda 2, 1 and 1, then we have lambda 1, 0, 0, lambda 2, then 1 minus lambda 2 minus 1, lambda 1. Okay, so if we want to find out the UK, we have a to the power k into u naught, right? So a to the power k into u naught, so e to the power k into 1 0. U naught was this vector, so uk is basically f of k plus 1 into f of k, this multiplied by a to the power k to 1 0. So a to the power k is basically this whole thing. Yeah, so in here, if we, so this is a, so if you want to find out a to the power k, then we need to just so from the previous part we saw that a to the power k is s lambda to the power k s inverse. So a to the power k should be, in this case the a to the power k should be 1 divided by lambda 1 minus lambda 2, then lambda 1, lambda 2, 1 1, then we had lambda 1 to the power k 0 0, lambda 2 to the power k, then we have 1 negative 1 minus lambda 2 and lambda 1, right? Yep. So if we put these values here, so we have a to the power k here, so if we put these values in here, we have 1 divided by lambda 1 minus lambda 2, then we have lambda 1, lambda 2, 1 1, we have lambda 1 to the power k 0 0, lambda 2 to the power k, then we have 1 negative 1 minus lambda 2 and lambda 1, then we have 1 and 0, right? So if we do the computation here, so let's multiply these things from the right. So let's use these two terms, so it should be 1 divided by lambda 1 minus lambda 2, so this would come here, this would come here, and you'll get a vector here which would be 1 and 1 and negative 1, right? So if you multiply this with this, you will get 1 minus lambda 1 minus lambda 2, this would come here, and you will have lambda 1 to the power k and minus lambda 2 to the power k, right? And you have this matrix as well. So lambda 1, lambda 2, 1 and 1. So now again, if you do this multiplication, you have if you multiply these two terms, you'll get 1 divided by lambda 1 minus lambda 2, and you get lambda 1 to the power k plus 1, lambda 1 to the power k plus 1 minus lambda 2 to the power k plus 1. Then you have lambda 1 to the power k minus lambda 2 to the power k. Okay, so the formula has, or the calculation has become really easy here. So this is f of k plus 1 and f of k. So if you compare these two sides, so if you further simplify these two terms, it would be lambda 1 to the power k plus 1 minus lambda 2 to the power k plus 1 divided by lambda 1 minus lambda 2 and lambda 1 to the power k minus lambda 2 to the power k divided by lambda 1 minus lambda 2. So these two terms. So now if we compare these two sides, so this is f of k plus 1, so the f of k plus 1 would be this, and f of k would be this, right? So we have our f of k would be lambda 1 to the power k minus lambda 2 to the power k divided by lambda 1 minus lambda 2. So we have lambda 1 had the value of 1 plus root 5 divided by 2, if I'm not wrong. So it would have 1 plus root 5 divided by 2 to the power 100. Oh, sorry, we're trying to find out the 100th term, right? So if 100 would be 1 plus root 5 divided by 2 to the power 100 minus 1 minus root 5 divided by 2 to the power 100, then 1 plus root 5 divided by 2 minus 1 minus root 5 divided by 2. Yeah, so we would have, I think if I'm not wrong, it would have 1 plus root 5 to the power 100 minus 1 minus root 5 to the power 100 divided by 2 to the power 100 into root 5. So this would be the 100th term of the Fibonacci sequence. So if you want to find out the 200th term, if you want to find out the 1000th term, then you just need to switch these values here. So as you saw, by applying the rule of diagonalization, this calculation has become really easy, right? So in the exam, if I give you a series, and if I ask you to find out a really big term of that particular series, I think you'll be able to find that using the concept of diagonalization. Okay, so this has another form, which I'll be discussing in the discussion class. So I think I should give you a homework. So let's say you have u naught equals to 1 0. That means the first two terms of a particular series is 0 and 1, and the matrix it follows is 1 2 1 0. So you need to find out the fk, right, where it follows the equation f of k plus 2 equals to f of k plus 1 plus 3 of fk. Okay, so you need to find out the fk. That means, like any term, if I want you to find out the, let's say, 1005th term, then you need to find out by using the concept of diagonalization, using this definition. Okay, so one problem from this type of from this topic would come in your semester final, inshallah. So I'll be further discussing this topic in the discussion class, so I want you to join in that class as well, and I'll see you guys in the class, inshallah. Okay, assalamu alaikum.